is we're trying to find things like derivative of L with respect to Q. We're trying to do dl with respect to Q dot, and then we're doing dt of dl dq dot. These things are easily handled by MATLAB using the symbolic toolbox. Okay, but first I need to introduce you to this command in MATLAB, and it's called diff. Okay, so if you want to find, so you put the name of the variable, in this case L, say for the first one, and you put Q, and if you do that, it'll actually give you dl dq. So as simple as that. Okay, so example would be if you want to find the derivative of f equals x squared plus 2x plus 1, then you'll just do diff f comma x. Okay, and then it'll give you the derivative of f. Before you do that, you however have to define. So by default, if you define x, it takes x to be a numeric value, right? 1, 2, 3. It doesn't know that x is symbolic. So you need to first tell MATLAB that x is actually a symbolic variable. So you use sims. Okay, and I like to put real here only because by default, when you assume it to be sims, it'll take x to be a complex number. It'll have an imaginary part. So if you see that your equations have a complex part, it's because it started assuming x to be a complex number. So I just put real, so that way x is understood to be real. So I'll show you how this works in MATLAB. But one more thing before we go to the next part is, if you want to find the value of f at a certain value, right, say at x equals 1, then all you need to do is say subs. Okay, you'll say, so let's call this some name. Let's call it df dx. Okay, that's the name given to it. Just say df dx at x equals 1, and so then it'll actually give you the value of um, df dx at x equals 1. So this should give you 2x plus 2, right? Derivative of x squared plus 2x plus 1. And then if you find the value at x equals 1, you should get 2 plus 2, which is 4. So let's check this a little bit later. So this is a symbolic differentiation. Now, what will happen also in this course is that sometimes you will not have access to f in its analytical formula. So you will not have analytical formula, and you will have to find the value of the derivative without using diff. Okay, in this case, what we do is we use a numerical differentiation by using either forward difference or central difference to find the derivative of a function. So I'm going to show you the numerical derivative of f as I've written here. But then once you have this formula, you can replace f with a code. By that I mean that when you do some complex calculations, you get f, as opposed to writing an analytical formula. And that will, and don't get confused right now, that will happen a little bit later when we do legged machines. We'll have f, which will be a code. It will not be a analytical formula, and then I can use this formula. But for now, let's see how to do numerical differentiation by finite difference. So here the key idea is that df dx can be written by, so the calculus formula is f x plus delta x minus f of x divided by delta x. So that's the formula where you take delta x is very small, right? So what you do is, if you want to find the derivative at x equals 1, you will write df dx as f of, say, 1 plus delta x minus f of 1 divided by delta x. So what it means is that you need to evaluate f at these points, 1 plus delta x, 1, and then divided by delta x. So what we do here is we take delta x to be really something very small, say 1e negative 3. So if you do this right, you will see that you'll actually end up getting the same answer I got earlier, 4. This is just one of the many formulas to find the derivative. There's another formula which people use, and that's called the central difference formula. It goes like this: x plus delta x minus fx minus delta x divided by, in this case, it will be 2 delta x. Okay, so you can put x equals 1 now and then do the same thing, put delta x equals 1e negative 3, x equals 1. And this is thought to be more accurate than the first one, which is finite forward difference. This is forward difference because you only find the derivative of x value at x plus delta x. This is called central difference because here you take plus and minus delta x. And usually these are adequate to do most of the calculations we'll see in this course. Okay, so now I'll head new file. Um, I always like to put CLC clear all. CLC clears the screen clear. CLC clears the screen clear all, clears all the workspace variables. Then I said if you write sims x real, and then if you define f equals x square plus 2x plus 2, and then if you do df dx equals diff x f comma x, then you should see that the answer is 2x plus 2. Let me save this file. Example sim derivative. Okay, so let's run this. So 2x plus 2 is right. And then if I want to find the value, then I do subs df dx at x equals 1. So either you can run this again or you can just copy paste this in the command window and you see the answer is 4. Okay, so that's the symbolic derivative. Now let's do the numerical derivative. So I do the same thing. In this case, let me first define this function f, which basically takes in fn x, and the function I defined was x squared plus 2 into x plus 2. And then since there's nested functions, I need to define the first one as a function. The difference between these two is that there's no function defined here because it's all a script, but here we want to define at least one function, right? And so you can't just define one function in a script. You need to put each of these blocks of code inside a function. So let's call this example sim numerical, and then save it, and then automatically it tells you that I want to save it as example sim numeric, which is the first one. So save it as it is, and now let's evaluate this. So df dx forward, as per our formula, it's going to be fn x equals 1, so it's going to be x plus dx. I've not defined dx, let me define that, and I think we decided on a small value, so let's take 1e negative 3 minus fn of x, the whole thing divided by dx. So that's one way to do it. The other way to do it is central equals, I'm just going to copy this, and then x plus delta x, x minus dx, and then this will be 2 times delta x. Okay, so hopefully both these answers should be equal to 4. Okay, there's an error. Yeah, so I did not return anything. I need to make it return something. Okay, so you see that the forward difference gave the answer to be 4.001, which is inaccurate by in the third decimal place, but the central difference gave me the exact value, which is 4.000. Okay, so in general, central difference is much accurate than forward difference. Okay, so one more thing before we actually get on to um, writing Euler-Lagrange equations using MATLAB. I need to introduce chain rules, which is going to be very important when we try to do differentiation involving multiple variables. In this case, we have x, x dot, y dot, and so on. Okay, so now we'll introduce what is known as the chain rule. Okay, so what's the chain rule? Well, first of all, let's say that if you have a function f1, and then we wrote down that function is f1 is a function of x, right? And so x squared plus 2x plus 2, we can take the derivative with respect to x, and that's easy. Now, what if I told you that x itself is a function of time? Okay, so the way you think of this is f1 is a function of x and x is a function of time. Okay, and then you're told to find df1 dt. Okay, so you need to find the derivative from f1 all the way to t, but then in between there's an x. So how do you do this derivative? So this falls in the realm of chain rule, where you first take df dx, so you go from f to x, and then you do dx dt. Okay, so this is the chain rule to differentiation. So here is an example. So if I told you f1 x of t is sine of x of t, where x is a function of time, then df1 dt is df dx dx dt. So that will be, first take the derivative of sine as a function of x with respect to x. So that will be cosine of x. And then you take the derivative of x with respect to time. So that's dx dt. So in this case, I have not told you what dx dt is, but that is not zero. So you need to keep it as dx dt. So that was one example. Okay. The other example is what if there was a function, let's say f2, and it was a function of multiple things. So in this case, let's say it's function of x of t and x dot of t. So position and velocity, if x is the position. Okay, so then you can again visualize this like this. f2 is a function of x dot, and that in turn is a function of time. So we need to find df2 dt. And so the way this goes is we first find f2 to x to t. So that will be written as df2 dx dt. And so you can see that the formula is the same as what we wrote down earlier. Nothing changes there. However, there's a second part which you cannot ignore. So this goes from f2 to x dot and then to t. So in the second case, you write with a plus sign df2 dx dot and then dx dot dt. Okay, so that is basically the chain rule applied to two variables. Here is an example. If I told you f2, which is x dot, is basically x of t times x dot of t, then if you're trying to do df2 dt, that's df2 dx dt df2 dx dot dt. And so for the first term, when you do the derivative of x times x dot with respect to x, you treat x dot as a constant. So then that will only be, the first part will only be the derivative of, so this is a constant, so the derivative of x of t with respect to x is 1. So x dot. And then, so by the way, x dot is dx dt. Okay. So then dx dt is simply again x dot, right? So I'll just write it as x dot plus df2 with respect to dx dot. So in this case, you treat x as a constant and x dot is the variable. So since you take the derivative with respect to x dot, this term, the second term is 1. And so you're left with x, the first term, times dx dot dt. So that's going to be basically the second derivative, so x double dot. So the answer is x dot square plus x times x double dot. Okay, so if you want to translate this to MATLAB, so remember f1 was x of t, then df1 dx, you'll write it as diff f1, sorry, df1 dt. You'll write it as diff of f1 with respect to x and then diff of x with respect to t. But really, x with respect to t is something which you'll be given, so you will just write it as x dot. And then if you want to find the f2, which is a function of x and x dot, then you'll write df2 dt as diff f2 with respect to x dot, plus diff f2 with respect to x dot, and then x double dot. So that's how you write down the formula for the. So first of all, just like here, I define x and y. So these are my symbolic variables: x, y, x dot, y dot, and then this is the acceleration. I do that because these are the things which will come up in the equations eventually. Then I define all the parameters which come in the equations. There is the mass, there is the drag force, and there's gravity. Okay, so this is the first step. Position velocity. This mirrors the Euler-Lagrange steps. So position and velocity are x and y, x dot, y dot. We don't need to specify anything here, but for, you'll see, for a double pendulum, you will have to actually write a formula for x and y in terms of thetas and so on. So here, nothing to be done. The second step is to write the kinetic and potential energy, okay, which is T minus V. T is half mv square, right? Half mv square is x dot square plus y dot square. Then you have the potential energy, which is mgy on the right side. The same thing is written here. Then the Lagrangian is T minus V. So I wrote that down. Okay, so now we come to the part where we actually write the Euler-Lagrange. Before that, what I did here was I wrote down this Qj. It's basically the force in the x direction, force in the y direction. So yeah, Fx, which is minus c times x dot, here c times x dot square root of x dot square plus y. So I wrote those down first, Fx and Fy. Okay, so now what I did was I first show you how to write this manually. So the equation which we're looking at is okay. So the Lagrangian here is a function of x, y, x dot, y dot. So you can imagine how many terms it will have when you try to do the derivative, when you do the chain rule. Okay, so the Lagrangian is, the Lagrange equations are d dt of dl dq dot minus dl dq equals q. Okay, I just wrote down what I wrote down earlier. Now we have to start writing each of these terms. Okay, so first of all, q is x and q is y. That's how we get the two equations. So first I did this for q equals x. So in this case, I would have dl dq dot would be dl dx dot, the first term here. So it's basically derivative of L with respect to x dot. And since I wrote the Lagrangian already, and then I have x dot which is defined, MATLAB just does the computation. Now comes the harder part, which is now I need to find the time derivative of this term, which is basically this over here. So it's d dt of this. Now we have this situation where, as I showed you, L, so dl dq dot is a function of x, x dot, y, y dot, and then that is a function of time. So when you invoke the chain rule, you will have four terms. First term will be the derivative of dl dx dot, this term, with respect to x times x dot, the first term. Then I take the derivative of that with respect to x dot, and then I'll have the second derivative, and then I do the same thing for y. So that's the chain rule. That's the four parts which come because of chain rule. And then the final piece is this term, which is the right hand side, dl dq, which is basically dl dx. Okay, so what are the equations? Well, the equations are d dt, this whole thing which I wrote down. Then there's dl dx, and then this q, I move it to the left side, so it becomes minus f of x. That way I can say that the equations of motion are EOM equals 0. Okay, I just moved everything on one side. I do the same thing for y. and that gives me the second equation, where here I have the equations involving y. And then finally, when I get from these two equations, I will get an expression for x double dot, the acceleration in the x direction, y double dot. And then if you if you say solve, then you actually will see that you will get the solution for x double dot, y double dot. Let me just run that first. Just comment this out. So if you check this with what I did last time, here's what I did in the class. The first one is the formula for x double dot. It's minus c times x dot, which is over here. This thing is the square root of velocity. Sorry, it's the velocity square root of x dot square plus y dot square, and then divided by m. And this is the formula for y. It has a minus g. Since there's a divided by m, it's actually minus g, the first term. And then you have minus c divided by m times y dot, which is here, times square root of x dot square plus y dot square. So you get the same answer as you get using hand calculations. Okay, that's the point. Now, what I did was, this actually is too unwieldy to write this. So to write L is a function of 4 things, and then do this manually takes a lot of time. So what I did was, and I do this all the time, which is I try to automate the process of writing this derivative without actually thinking, oh, there are 4 terms in L which I need to do chain rule with, and so on. So what you do is, essentially, if you take this code, okay, where you identify how many free variables are there. In this case, there are 2 free variables, one for x, one for y. Then this code will automatically generate the equations, 2 equations, 3 equations, 4 equations you want, provided you specify what q is. In this case, q is the degrees of freedom x, y. Q dot is x dot, y dot, and then q double dot is the acceleration. So once you have these, you specify these things, which will change depending on your problem. You just need to copy paste these lines of code, and then it will actually generate all the equations for you without you have to actually think of how many terms are there and so on. So let's run this, and you'll see that the answer is, um, well, so, my bad. Actually, you do need to write the 4 terms here. The 4 terms actually appear over here. Okay, q1 q dot, but you don't have to write it. So in this case, there are 2 equations, and you don't have to write those 2 equations 2 times. That's all it this particular automation enables you. You don't need to write that 2 times. You just write it once. If there are 4 equations, then you just write a loop for 1 through 4, and it'll take care of it. However, you do need to write uh, the corresponding term like this. Actually, there should be a way to automate this too if you want to. That is, you don't need to write this 4 items. You could write another for loop if you wanted. I just thought that's going to make it look too confusing, and so I don't really write it as 2 for loops. But you could potentially automate the DDT term also. Okay, so if you look at this now, you'll see that the answers I get from the first part agrees with that of the second part, which is basically the automation part, and this is the second part of the equation. So that checks out. The equations are the same I got, and then you can now proceed doing the simulation animation. Okay, questions?